Hey everyone, and welcome to another Explainer. I am absolutely pumped to have you here today because we're going to be diving into something truly fascinating, the intersection of artificial intelligence and Earth system sciences. You know, our planet is incredibly complex. It's dynamic, and let's face it, sometimes wildly unpredictable. But what if we could actually harness the most advanced computing systems ever created to finally understand and even forecast its deepest patterns? So here's the million-dollar question. Can artificial intelligence truly predict the Earth? It's a pretty provocative thought, right? I mean, for centuries, we've been trying to predict the world around us. We've gone from ancient philosophical reasoning to these incredibly complex modern scientific models based on strict physical equations. And sure, we've gotten pretty good at telling you if it's going to rain this weekend. But seasonal forecasting, predicting extreme sudden events like catastrophic floods or massive wildfires months in advance, that is still a massive, massive challenge. Today's Explainer is all about investigating how deep learning is stepping up to the plate to solve this exact problem. To get a solid grip on this, we're going to follow a quick 5-part roadmap. 1. The big data deluge. 2. Traditional machine learning limits. 3. Enter deep learning. 4. Challenges for Earth AI. And finally, 5. The hybrid modeling future.
All right, let's jump right into Chapter 1, the big data deluge, and how we cope with the Earth's data. As you'll see here, our current data ecosystem is basically a massive, non-stop streaming network. We have all these diverse observation systems constantly beaming information down to us. We're talking everything from remote sensing satellites way up in orbit to autonomous sensors floating at the bottom of the ocean. The ultimate goal, of course, is to move from all that raw, messy data to digestible knowledge. But right smack in the middle, we hit a massive bottleneck, and it's defined by the 4 Vs.
Let's break those 4 Vs down real quick, because the scale we're talking about here is just staggering. First is volume. Earth system data already well exceeds 100 petabytes. To put that into perspective, just one single climate model dataset, CMIP6, is estimated to reach up to 30 petabytes on its own. That's an incomprehensible amount of data. Then there's velocity. This data is moving fast. It's growing by more than 5 petabytes a year, with some sensors firing off readings multiple times a second. Third is veracity. We're dealing with everything from simple 1D point measurements to crazy complex 4D spatio-temporal models. And finally, veracity. This data has inherent uncertainty. You've got observational errors or even just missing gaps because a regular old cloud happened to be blocking a satellite's view. Simply put, our ability to collect data has totally outpaced our ability to actually assimilate it.
Which brings us to Chapter 2, traditional machine learning limits, or why the old tools are starting to fail us.
Now, traditional machine learning is fantastic when we're talking about spatial or static prediction. If you have sparsely distributed point measurements of dirt and you want to use a model like a random forest to map out soil types across a whole region, traditional ML does an outstanding job. It knocks it out of the park. But here's the catch. The Earth isn't static. It is highly, highly dynamic. When we try to predict spatio-temporal events, things that are physically moving and changing over time, like the atmosphere or ocean currents, traditional algorithms really struggle. They just don't inherently grasp that context of space and time. And when you're dealing with the atmosphere, missing that context is a total deal breaker.
This limitation becomes super obvious when we look at something called memory effects. Think about predicting a wildfire or a drought. A drought isn't just about whether it's sunny today, right? It's heavily dependent on the fact that it literally hasn't rained for the past 3 months. The system essentially has a memory of its past states. Traditional machine learning often just ignores these interactive effects over time, unless a human scientist sits down and painstakingly handcrafts those specific features to feed into the model.
On top of that, traditional ML struggles with spatial context across massive distances. In Earth sciences, we call these teleconnections. A classic example is how predicting an El Niño event way out in the Pacific Ocean can actually help us predict rainfall, snowfall, or temperature patterns in North America weeks or even months later. The Earth's climate anomalies are physically linked across thousands of miles. Trying to teach an old-school algorithm to look for these distant, invisible threads, it's just incredibly difficult.
So, what's the solution? Chapter 3. Enter deep learning, the true catalyst for change.
Deep learning architectures, specifically artificial neural networks with many hierarchical layers, are uniquely equipped to extract those tricky spatio-temporal features completely automatically. Unlike the older methods, deep learning doesn't need a human to hold its hand and design specific features to track, say, the geometry of a hurricane. It can look at the topology, the symmetry, the visible eye of the storm, and automatically learn these abstract features from raw, messy, interconnected data.
It finally views the Earth exactly as it is, as a giant, interconnected, dynamic system.
And what's really cool is how translatable deep learning is to geosciences. The exact same tech that companies use for object recognition, like finding a car or a face in a photo, can be used to classify extreme weather patterns in a climate model. Video prediction, where AI guesses the next frame of a YouTube clip, is mathematically super similar to precipitation nowcasting, basically guessing where a rainstorm will be 2 hours from now. Even language translation networks are being used for dynamic time series modeling. The underlying math of predicting the next word in a sentence is literally helping us predict the next fluctuations in global temperatures. How wild is that?
But of course, it's not all smooth sailing. Let's look at Chapter 4, Challenges for Earth AI and the Roadblocks Ahead.
Applying this cutting-edge tech to geophysics brings up 5 major hurdles. First, interpretability. We really can't have a black box making huge climate predictions. Scientists absolutely need to understand why the AI made its choice. Second, physical consistency. Deep learning models might predict something that statistically perfectly fits the data, but completely violates the laws of physics, like mass or energy conservation. We can't have that. Third, as we covered, the data itself is complex and uncertain. Fourth, we have limited labels. And fifth, the sheer computational demand of processing petabytes of global data is just massive. Let's actually zoom in on that fourth hurdle for a second. Limited labels. Deep learning and computer vision totally exploded because of databases like ImageNet, which literally has millions of human-labeled photos of cats, dogs, cars, you name it. Identifying a cat is trivial, but labeling an Earth event? That is highly conceptual. Think about it. When exactly does a drought officially start? When does it end? What mathematically defines its intensity? We simply do not have massive, perfectly labeled datasets for Earth systems because the definitions are fuzzy and change depending on how you measure them. So how do we solve these roadblocks? How do we make sure our AI doesn't break the laws of physics while it's learning from all this chaotic, unlabeled data? That leads us right into our final chapter, Chapter 5, the hybrid modeling future. This is the ultimate resolution. The future of this whole field lies in the synergy between physical process models and data-driven machine learning. Historically, scientists relied on either strict theoretical equations or pure data statistics. But the future, it's about combining them. We can actually use machine learning to swap out poorly understood weak submodels, like trying to simulate the exact biological regulation of plant water transport, while keeping the strict, unbreakable physical equations for things like energy and mass conservation right alongside it. We can even use AI to analyze the mismatches between our physical models and the actual real-world observations to correct built-in biases. It's a best-of-both-worlds scenario. Conceptually, you can think of this hybrid approach in 3 easy steps. Step 1, a super powerful neural network ingests that massive data deluge we talked about, extracting those complex spatio-temporal patterns. Step 2, rather than just spitting out a raw and verified prediction, that data passes through a physical constraint layer. Think of it as a bouncer that enforces the laws of thermodynamics, gravity, and mass balance. Step 3, the system finally generates predictions that are not only highly data adaptive, but completely physically plausible. So we are literally deepening AI architecture by adding physical layers to it. For instance, you could have a deep learning network that first learns the highly complex motion field of ocean water based purely on past temperatures. But then, a physical warping model is applied as an actual, literal layer on top of the network to predict the future temperatures. In another approach, an AI might predict plant behavior based on weather data, but a strict physical diffusion equation takes over to calculate the actual water loss. It's an incredible partnership between computer science and earth science. Which leaves us with this final thought. Will the interplay between data-driven machine learning and theory-driven physics fundamentally change the future of scientific discovery? Looking at the evidence, the answer seems to be a resounding yes. By fusing the pattern-matching brilliance of artificial intelligence with the unwavering absolute laws of nature, we are creating a totally new generation of hybrid models. Models that don't just guess at the weather, but genuinely understand the Earth system, promising to unlock the deepest secrets of our planet's future. Thanks so much for joining me on this explainer. I hope you found it as mind-blowing as I did. Keep questioning, keep learning, and I'll catch you in the next one.